Hello viewers. Today I'd like to do an explanation on 120 240 volt single phase 3-wire services. And this is a very controversial topic on YouTube right now, so someone is probably going to run to the dislike button now. But since I have a litany of these transformers, I thought I would wire them up to simulate a residential service. But before I do that, let me just explain how these transformers work. As you can see, one single bushing on top, which is where, in this case, since this is a 13.2 kV transformer, a 7620 volt line would come in and then go to ground. Single phase, but there are 3 low voltage bushings. Each are 120, 120, 240. A lot of people refer to this as the center tap. However, this is not a center tap in the transformer. On transformers larger than 100 kVA, so usually 167 kVA and above, there'll be a bushing here and then 2 bushings here, and the other one on the end. And a utility will usually series or parallel them depending on what voltage they want out of the transformer. Now, let me spin this around, and bear with me because it weighs more than twice as much as me, but I'd like to show the specifications plate. As you can see, the high voltage is rated at 13,200 Y7620. This is for a 13.2 kV system. The reason why the coil of the transformer only sees 7,620 is because of the square root constant, in which I'll do a diagram later just to visually show how that works. As you can see, the low voltage is 120 240. Keep in mind that that is an additive, so 120 plus 120 equals 240. 7620 plus 7620 does not equal 13200. As you can see in the schematic of the low voltage, you have one high voltage coil and 2 low voltage coils. Each are good for 120 volts. In this factory configuration is shown as a series connection, so you have 1, 2, and 3 outputs, 120 and 120, and the center one is always tied to ground on a Y transformer. So it's a 13200 ground Y, so that's always tied to neutral ground. There's also a second configuration where you can parallel the 2 low voltage windings just to get 120 volts out. Utility companies do this a lot with 120, 208 Y systems. Using residential transformers, they could be banked together for a 3-phase service. You could also bank a whole bunch of single-phase transformers to get a 120, 240 delta with the 208 hot leg. Here is a vector of a 13.2 kV system. As you can see, the phase to phase voltage is 13200. But if you were to measure out the vector and do the hypotenuse calculation in reverse, the phase to ground would be 7,620 volts. That is where the uneven numbers add up, such as 277 plus 277 equals 480. As in here, it would be an additive system, so 120 plus 120 equals 240. In a 3-phase system, it is to the 1.73, which is the square root of 3. Such as a very common voltage is 12470 Y 7200, and that dates back to the days of the Rural Electric push, where most systems that were installed were a 7200 delta, so 7200 between each phases. But then people realized that you could connect them in a star configuration, 7200, 7200, 7200, and it would be 12470. It'd be more power, and you wouldn't have to upgrade the insulators. Another common voltage is 34500Y 19920, 33260Y 19200, 4160Y 2400, 24940Y 14400, 8320Y 4800. Now in a delta, a 120/240 delta 208, there are two transformers, single phase, banked together. My local utility company uses one transformer to get the third leg, which is the 208 from phase to ground, 1.73, again, constant. And then they have a larger single phase which feeds single phase loads. The bank, this would be the single phase transformer. This would here would be tied to ground, 120/240, and next to it they would tap off this bushing here, go to second transformer, and then isolate this neutral here. So they'd put a cap over it, and this would not be touching ground, and then this would be the 208 leg. They would use two phases off the high voltage to do that. Here is just another specification of what's inside the transformers. You can have a dual bushing transformer. So you can see they made improvisions for this transformer here in the factory. If it was a single or a dual bushing, say if this was a 7200 volt transformer, you could connect it Y to a 12470 system, or phase to phase on a delta system, be single phase on the low voltage side. And in a subtractive polarity transformer, which is what most commercial transformers are, such as this one, as it has a coil voltage of 14400, which is not usually on residential streets, more of a commercial voltage. Electricity in an instantaneous current vector would flow to ground, and then both low voltage coils would flow in the same direction to ground. So if there were no load on one phase, the voltage instantaneously would flow out of the neutral, go through the load, and back to this tap here. But since alternating current is always going back and forth, it does not matter which one would be grounded. This here could be connected to ground, and then you would have a 120 or a 240, and they would be 120 volts apart. But this one would always be 240 volts to ground. In the US, there is no such thing as 240 volts to ground. It is phase-to-phase residential, and then 120 to ground on both legs. Now, I know I'm going to get dinged for saying neutral and ground interchangeably. However, on the distribution side of the world, neutral and ground are the same thing. This on a Y system is always at ground potential, and it's the neutral. It is also a current carrying conductor. Unlike in a residential system, the ground is not a current carrying conductor. That's why this is 14/2 wire, because the number of wires that is counted are current carrying. So you have a current carrying hot wire and a current carrying neutral wire. The ground does not carry current ever in a residential system. However, this wire here on the utility side always carries current on a single phase load. If this wire were to be cut and disconnect from the source, which is this transformer here, this whole transformer and everything attached to it would become live at 7,200 volts. And that's why it's always crucial that grounding is taken care of. Now I'm going to go inside the meter base here and just explain the voltage and how it works in a residential setting. However, this is just a demo setup, and you never want to go into your meter box or really work with anything above the main breaker. As you can see here, the reason why is this impedance right here. That is how much current this transformer will flow on a dead short. And on the low voltage side, if you were to short out these two terminals, according to that 1.07% impedance, there would be short circuit current of 1800 amps at 240 volts. And that will definitely ruin your day. So, whatever you do, leave this side to the professionals. So right now, I'm going to open this meter and show what is inside. And to get inside, you have to cut the utility seal. Once the locking ring is off, the meter can simply pull out of the socket. As you can see, now that the meter is out, I will energize the system and stay away because I personally don't like to be near 7,200 volts when it's live. But turning on, you can hear the transformers hum, and the socket there is now live. And just to do an arc to show that this is live at more than residential voltage. So with a multimeter, if you were to go in your meter box, now keep in mind that this is on a current limited circuit. If I were to short this transformer out just connected to 240 volts, it would blow the transformer on the street because the transformer that powers my house is a 10 kVA, 5 more kVA, but from phase to phase, you see 244 volts. Now, from neutral, ground, to both legs, 121. And 121. As you can see, it's a division of 2. So, again, phase to phase, 240. Phase to ground, 121. 121. So you can see this here is a additive polarity transformer. So the current goes in a circular motion instead of directly to one side like in a subtractive. This comes in, goes to ground, and then H1, L1, L2, and L3. Now here I have a standard socket, however it would not make a code inspector happy. That's rusted, but top socket and bottom socket are on different legs. So this is on one 120 leg and another 120 leg. Together from the two hot plugs would make 240 volts. Meter is back in the socket. Just to like to show that is true. See, 120 and 120 the top socket. You'll actually touch the contacts in the outlet. But from hot to hot, .240. Now, the reason why this is done is I shall now plug in a few appliances to demonstrate. Now I will plug in a 1 kilowatt space heater. You can probably hear it running in the background. And I will plug in an iPhone. You can see that it's charging. You can also see now that the meter is spinning. Now, the iPhone obviously does not use as much power as the space heater. And what is happening now in the circuit is that there is a greater load on this side of the transformer. So the neutral is absorbing the excess power from the space heater, while the iPhone, on the other hand, is getting less power. However, some power that is going through the space heater is going back into the X3 terminal, because this is an additive transformer. The neutral is carrying the excess power that the space heater is using. As I will demonstrate, a very vague amp meter can measure how much current each leg is pulling. You can see about 50 milliamps for the iPhone, 60, maybe 55. It's not that accurate. And the leg that the space heater is connected to is pulling 8.2 amps. So a lot of people say that there's an extreme side that says the neutral is not used at all. It is just for a lightning suppression, and there's people who say that it carries back all the current. But as you can see, it's pulling 8 amps. Not the full though, not the full 8.4 amps. This is a very inaccurate multimeter, but it's balancing the unbalanced load from both terminals. And if we go to the high voltage side, which I don't advise doing, we could get measurement on the high voltage ground side. An electrical glove. This is very important because this neutral will become live once it is removed. You can see there will probably be a spark. And now the space heater has shut off. However, it has not fully shut off. As you can see, the iPhone is still charging. Now, what is happening is that the space heater and iPhone are in series with each other. So the power comes out, goes through the space heater, into the iPhone, and back to the transformer. Without the neutral conductor, which is there and live now, there is no way for the excess current that the space heater will use to get back into the transformer. So the iPhone is limiting the circuit to the amount of power that it can draw. And as you can see, you'll be able to see the meter is spinning very slowly because it has just the load of the iPhone and space heater on it. Now I'm not going to reconnect this while it's live, so I will disconnect the system and then put the neutral back. As you can hear, the space heater turned back on and the iPhone started charging again. As you can see, both loads now can operate independently from one another. However, if the neutral was not there, you would have to put two 120 volt appliances in series for the 240 volts. And while I still have this going, just a neat little trick with a non-contact pen tester. As you can see, the ground is the ambient voltage. You know, it's not going to pick up the ground, but it'll pick up hot wire, another hot wire. But with 7200 volts inside, once you get above that shielded area, it's out in the open, you know. Just thought I'd show you that little trick. But that's it for this video. Catch you in the next one.